Aaron is an astronomer at the National Science Foundation's National Optical Infrared Astronomy Research Laboratory, which is affiliated with the Arizona's Kitt Peak National Observatory. For over 5 years, Aaron has been a core member of the DESI Instrument Commissioning and Target Selection Imaging Survey teams. Aaron specializes in building astronomical maps using large data sets at visible and infrared wavelengths. He received a bachelor's degree in physics from Stanford University and earned his PhD in physics from Harvard University before joining NORLAB's scientific staff. He was a NASA Hubble Fellow at the National Optical Astronomy Observatory in Tucson, Arizona. So please, can you give us the Mexborough and Swinton Astronomical Society way of welcoming Aaron to our meeting tonight? Well done, Aaron. Thank you.
Thanks. So should I share my screen or is there more to come?
No, you can share your screen now.
Okay. Okay. So I'll just get going from here. So the title of my talk, as you saw in the program, is DESI, the largest ever 3D map of the universe. This is a nice picture showing here the telescope, the 4-meter Mayall telescope at Kitt Peak National Observatory, about an hour outside of Tucson, Arizona. And the Mayall telescope is where DESI, which is sort of a hardware system including spectrographs, has recently been installed. So, you know, I go here a lot, at least not during the pandemic times, but to go observing, for example, for DESI and other things. So it's a great place to visit if you're ever in the American West, American Southwest type of area, California, Arizona type thing for a trip or a vacation. So what is DESI? It's an acronym that stands for Dark Energy Spectroscopic Instrument. In summary, it's a new spectrograph for Kitt Peak's 4-meter Mayall telescope. So, you know, in optical astronomy, you have typically 2 different types of projects or hardware that you could do. You could have imaging, which just takes 2-dimensional pictures of the sky. I'm sure a lot of you do that type of stuff with your own telescopes. And then there's also spectroscopy, where you're spreading out the light from individual astronomical sources into its component wavelengths, you know, blue, green, yellow, red, etc. And that's what DESI is all about. It's about doing spectroscopy, but it's what we call massively multiplex. So it can take 5,000 spectra at once, and that's what's really novel and powerful about it. And so not only is DESI a spectrograph, but it's a lot of new hardware that's totally revamped this Mayall telescope, as you can see in the picture on the right. We've actually mounted a totally new top end and corrector that is about 10 tons in total on the prime focus of this telescope, and taken everything that was on it off, everything that was on previously off. So DESI, although it's a cool telescope and cool set of hardware, it's sort of more than that. It's kind of an epic quest to understand the composition and evolution of the universe at a fundamental level. So trying to answer big questions like, what is dark energy? What is dark matter? Is general relativity really correct? And the unifying theme here is that we can address all of these big questions by mapping the universe in 3 dimensions better than we ever have before. So that's really what DESI is all about. So I just wanted to go into a little bit more of what it is from the physics cosmology side that we're trying to do with DESI in terms of how we're going to measure the composition of the universe better than ever before. So we start out with what we do know, which is what we call ordinary matter: protons, neutrons, electrons, atoms, molecules. I believe this is a caffeine molecule shown here. And these are the building blocks that make up everything we can see and that we are familiar with in, you know, our everyday lives. Of course, these same components that we know well also make up things like planets, stars like the sun, and galaxies, which this one here consists of many tens of billions of stars. And so this is the well-known M51 Whirlpool galaxy shown here. I'll show a picture later that we took through the DESI corrector of the same object, which is kind of neat to show for comparison. So what we already know before DESI is that there are galaxies everywhere if we look out with sensitive enough telescopes all over the sky, and they form into what we call this filamentary cosmic web type structure, where they're not just totally randomly distributed, but there are these sort of overdense and underdense regions that have to do with how the gravitational collapse of matter is happening throughout the evolution history of the universe. So what does shape this cosmic web that we see even now before DESI? And the answer to that is the history of the universe is what shapes it. So in our current, what's called the lambda CDM model that we use as astronomers and cosmologists and physicists, we have a big bang that starts out. So everything starts out in a very dense and hot state, and that kicks off the expansion of the universe that is continuing to this day. About 100 seconds after the Big Bang, we get the first atomic nuclei forming, and then about 370,000 years later, we get the first atoms forming. So these are hydrogen atoms. So we get the nuclei actually are able to combine with the electrons in order to form, for example, hydrogen. Going to much longer timescales now, so 500 million years into the history after the Big Bang, we have the first stars start forming, and at a similar time, we have the most distant known examples of galaxies at around 0.7 billion years after the Big Bang. Then in the time period of 3 to 6 years after the Big Bang, we have the peak epoch of star and galaxy formation. And then basically since then, we've had just the continued expansion of the universe. Galaxies are continuing to exist and more of them are continuing to form. And then we finally reach today, which is 13.8 or so billion years after the Big Bang. So we exist in the present day, but we can, by looking at very distant galaxies, we can effectively see further back in time the further away we look, which is kind of neat and is an important part of what DESI does. So just to put a little bit of a video to these words, this shows a simulation of how cosmological structure in terms of galaxies forms over time. And so you can see that there are these dense regions that are the galaxies, and then they're forming into these sort of filamentary-like structures that connect across multiple galaxies. So you have small clumps growing into larger clumps on billion-year timescales. And then you also have additionally galaxies becoming bigger by merging and then joining into galaxy clusters and groups. And this simulation was done at the Institute of Computational Cosmology in Durham. And Durham is actually one of the main UK partners of the DESI consortium. So I thought that was kind of a neat connection there. So here's how I would summarize the state of what we know as astronomers and physicists about cosmic structure in the pre-DESI era. So galaxies and clusters are moving too fast relative to the amount of ordinary matter we can see. That is, just like planets orbit around stars, galaxies orbit around the centers of galaxy clusters. And they're actually orbiting too fast to be accounted for by just the mass that we see in terms of the stars that we can account for in these galaxy clusters. So this tells us that there must be a lot of gravitating, what we call dark matter, in these clusters and in the cosmic web that isn't directly visible to us. And the other really salient thing that we noticed, this is something that was discovered about 25 years ago in the late 90s and was the subject of a Nobel Prize in 2011, is that galaxies are moving away from us and one another at an accelerating rate. And so that's weird because we expect gravity to slow down the universe's expansion over time by pulling things together, even though they're trying to spread apart based on this initial kick of energy they received from the Big Bang. And so this tells us there must be something that we call dark energy, for lack of a better term, that's acting to counter gravity and to speed up the expansion of the universe. So to summarize this a little bit more quantitatively, dark matter is about 5 times more of the universe's energy content than the normal matter that we can see. And dark energy is 3 times more than even the dark matter. And so roughly speaking, what this is saying is that we don't understand about 95% of the universe's content in terms of its energy. So that really motivates us to want to, of course, try to learn more and figure out some of these major mysteries with experiments like DESI coming up in the near future. So how can we best map cosmic structure with things like DESI? We can't, unfortunately, directly see the dark matter or the dark energy. That's kind of why we call it dark. But we can see the galaxies that have the stars in them. We can see them out to many billions of light years away from us. And so the convenient and useful thing is that galaxies are distributed like the underlying dark matter, and we can see the galaxies. And so we can use the galaxies that are far away from us as tracers of what's going on with the cosmic structure in the dark matter and the cosmic expansion that's being driven to accelerate by dark energy. So I just wanted to show a few fun examples from the surveys that we've been doing to try to select the galaxies that DESI will look at spectroscopically, to highlight just how important it is in order to get this third dimension that DESI critically gives us that isn't accessible by just taking pictures of the sky, for example, in 2 dimensions. So here's an example of one of these images that we're looking at. Mapping galaxies in 2D is relatively straightforward. You just take lots of highly sensitive pictures of the sky, but it's also very limited. We don't actually know with perfect certainty which sources are actually stars and which are the galaxies. And we also need to know this crucial third dimension of how far away each galaxy is from us in order to be able to actually make a 3D map and to figure out the structure of the universe. So here's a fun example that I sometimes like to show about this. With 2D images, you can sometimes, but not always, guess correctly when galaxies are nearby to each other. So this is, again, another image from our surveys that we've done, imaging the sky to pick DESI's targets. And these 2 galaxies are confirmed by follow-up, the 2 with the arrows, to be part of the same cluster. So they're basically the same distance, and they're also close to each other on the sky. And you can sort of guess that because they have very similar colors, and their fuzzy extendedness also just looks similar by eye. But this approach doesn't always work so well. So here's an example that I like to show for this. These 2 sources both look point-like. They're very nearby on the sky. They have very similar color and brightness. So this might lead you to guess, even for me as someone who's a professional astronomer with a PhD, you might guess that this could be like a pair of co-moving companion stars in the Milky Way, for example, because it just sort of looks like that by eye. But that would be a very wrong assumption based just on the 2-dimensional information we have from this picture. In fact, the object on the left is a distant quasar, which is a special type of galaxy with a very bright black hole in the center. And the object in the upper right is actually a star in the Milky Way. And so the distance ratio of these 2 objects is actually like a factor of 5 million. So you definitely don't want to just go based purely on this 2-dimensional image and think that that tells you what you need to know about the distances of the objects, because that'll turn out to be incorrect. So this is where DESI really comes in with the power of the third dimension, because DESI will measure spectra for tens of millions of galaxies over the course of its 5-year survey. Again, it can do this so well because it gets 5,000 galaxies at once. I'll get more into a little bit of the technological aspects of how it's possible for us to do that a little bit later in this talk. And each galaxy spectrum can tell us that galaxy's redshift. And so the redshift is kind of, you can think of it like the Doppler shift of, as everything in the universe expands away from each other, the galaxies that are further from us will look like they're receding from us faster, whereas the closer ones will look like they're receding relatively slowly from us. And so DESI directly measures the redshift by gathering the light as a function of wavelength for about 35 million galaxies. And so that gives us this redshift, which is sort of a proxy for distance and time, although unfortunately the redshift still isn't a true third dimension of the distance itself. So that's the final piece we need to sort of understand the way that DESI's scientific physics and cosmology will work in practice. Right, so the redshift unfortunately isn't a true distance. The relationship between the redshift and the distance depends on the amounts and properties of the dark energy, dark matter, and normal matter that combine to make up the energy content of our universe. And so by measuring the distance versus redshift, we can therefore learn about the dark energy and the dark matter and the formation of structure and the evolution of the universe. So don't worry too much about the details of this plot, but it's just a schematic showing how this works. So on one axis is redshift and on the other is distance. And the point is just that if you have different compositions of the universe, like only normal matter, the type that we can see, or only dark energy or only dark matter, you'll trace out different lines within this plot as a function of redshift. So this is called a Hubble diagram. And so DESI is going to make its own version of a Hubble diagram, but better than other surveys have been able to do before. But this leads to sort of the key last bit here, which is how can we calibrate the galaxy redshifts, which is what DESI will actually measure in its spectra, to distances. And that's a very, very tricky thing to do. So there's a couple approaches to this. You may have heard these terms. Standard candles and standard rulers are the two sort of different ways you can go about doing this. So a standard candle is a type of cosmic source that always has the same intrinsic brightness. So if you put it 2 times further away from us, it'll look like it's 4 times fainter. So I don't know if your society has ever had a speaker from the field of supernovae, for example, but supernovae are an example of a standard candle source class that has been used to do cosmology in the past. And of course, that's now how we know about the existence of dark energy, and that's how dark energy was found and was awarded the Nobel Prize in 2011, was by using supernovae in the distant universe as standard candles. DESI actually takes kind of the opposite approach. So it uses a standard ruler approach in order to measure distances. So a standard ruler is defined as having a fixed physical size. So if you put it twice as far away from us, that means it looks half as large in angular size. And DESI uses this type of approach rather than the standard candle approach. Okay, I think this is probably the most technical slide in the whole talk, so bear with me. But DESI's standard ruler is called the BAO, or Baryon Acoustic Oscillations. And so BAO has a fixed physical size of 100 megaparsecs. So 1 parsec is 3.26 light years. So 100 megaparsecs is a huge span of the universe. So this is why, in order to do BAO physics and cosmology, you need to be mapping huge volumes of the universe. And so again, sort of going back to the Hubble diagram type of thing that I showed before, there's a different trend of angular size versus redshift for different models or compositions of the universe. So as a function of redshift, your BAO ruler will look a different size depending on what is in the universe. And you can see from the y-axis of this plot that the angular sizes we're talking about here are many degrees. So these are big swaths of the sky that we have to map out in order to have any hope of doing this type of BAO cosmology. And the other thing I noticed is just that DESI is really pushing this BAO technique that's been tried before into a much, much higher redshift regime than has been done in the past. And you can see that as you push to these higher redshifts above, say, 1, that's where the models start to show more differences from one another, the blue, the green, the white lines, depending on the composition of the universe. So it's very valuable from the sort of fundamental physics perspective to be able to do this BAO type of work, but at higher redshifts, so with fainter and more distant sources, the way that DESI is doing it. Here's the way that I would try to explain by analogy the BAO. So sorry, I can turn off the sound there of this clip. But the way that you can think about the BAO standard ruler is that in the early universe, everything was this sort of dense fluid, and there were slightly overdense regions in that fluid just through random chance. And those would send out sound waves that ripple out throughout the rest of space. And the reason that these sound waves can propagate is because the universe was so dense. But of course, the universe continued expanding, and the density as the universe expands goes down and down and down. And so at a certain point in time, these ripples get frozen in to the density distribution of the universe, and we can still see them to this day. And so that's the trick that the BAO cosmology uses, is that we have these special frozen in ripples in the distribution of galaxies that we can still detect very subtly today by making large sky maps. So here's a little bit more of a video illustrating the BAO. So, you could think of this as the surface of your water now, but really this is like the density of matter in the early universe. And there are all these little random peaks going on, and they're all emitting their sound waves that are propagating outward in these shells. And they're overlapping with each other. So you don't really see one of these nice rings in practice. You just see a sort of mess statistically of lots of overlaps. So here's what it would look like as we sort of see it today, where we're looking out onto the sky and we see these overdensities and underdensities of galaxies. So the rings with their bright centers are the overdensities of galaxies that we would see today. Right, and so the galaxies are starting to populate this underlying dark matter here, where you have extra galaxies at the centers of these rings, plus in the shells surrounding them. And so what DESI is going to do is it's going to map the three-dimensional positions of all these galaxies, and then it's going to sort of look at the distribution of the separation between these galaxies and make a histogram of that separation. And with millions of galaxies, you have lots and lots of millions of pairs. And so you build up nicely this histogram by taking all the possible pairs. And what you'll see is that you have a sort of distribution where galaxies tend to cluster together. So there's the peak towards the left, but then you get the secondary BAO peak, which comes from the shell of extra galaxies from these sound waves in the early universe. And so the BAO peak is what DESI uses in order to have a standard ruler that gives us both redshift and distances. And that will allow us to make very powerful statements about the content of the universe and what's going on with dark energy. So just to summarize the motivation before I get a little bit more onto the astronomy instrumentation type part of how we actually do this with DESI in practice. There's quite a lot that we don't understand yet about the universe, especially with dark matter and dark energy that make up 95% of the universe, and we really have no clue what they are. So normal matter, the distant galaxies, can be used to trace the large-scale structure of dark matter and expansion of the universe. DESI will make the best ever 3D map of the universe with an emphasis on understanding dark energy, and specifically dark energy using this BAO standard ruler technique. So now I just wanted to mention some of the key advantages that DESI has that make it possible for it in practice to map the universe 10 times better than anyone has done before. So DESI's predecessor, you may have heard of through some of these events or otherwise. It's a well-known survey. It's called the Sloan Digital Sky Survey, or SDSS. And SDSS basically obtained a few million galaxy redshifts over the course of, let's say, 20 years now. Started gathering spectra in the early 2000s. For reference, DESI is looking to get 35 million galaxy spectra in 5 years. So clearly DESI has some advantages and is doing some things better. So there's sort of three main key advantages that DESI has over Sloan. First of all, DESI gets 5,000 spectra at once, which is a huge number versus 1,000 for SDSS. The Mayall telescope that we use here in Arizona is 4 meters versus 2.5 meters for the Sloan telescope, so we have a bigger telescope. You also have some other more minor advantages, like the sight in terms of its seeing the atmospheric turbulence is better at Kitt Peak than it is for Sloan, which is at Apache Point in New Mexico. And then another key one is that DESI has what we call robotic positioning of its fibers, whereas SDSS has manual plugging of plates. So I'll show some pictures and videos that explain a little bit more what these terms mean. But basically, DESI has this new technology where each galaxy is placed on a fiber optic cable tip, and those fiber optic cables are moved around within DESI's focal plane by what we call robotic positioners. So you take one exposure with DESI and you're looking at one galaxy, then that positioner moves around slightly after you've slewed the telescope to your next location so that it's pointed directly at some different galaxy. And being able to reconfigure like that in a matter of a minute is a huge advantage. So all of this combines to be something like a factor of 10 improvement, certainly a factor of 10 if you just consider the raw number of objects that will get spectra of with DESI. So what you're seeing here on the bottom is a visual illustration of the DESI robot positioner, what we call patrol radii on the sky. So each positioner can move around a circular region that's about 3 arc minutes in diameter, as shown here. And so there's lots and lots of galaxies and stars within that. And so the trick is to get DESI's fibers positioned exactly on the right galaxies within those patrol radii. Just to give you a sense of another reason why DESI is able to map such a huge part of the universe so efficiently, this is the DESI field of view. It's about 3 degrees in diameter. And for comparison, I put the full moon on here. And so again, you're mapping a huge amount of the sky at once, thanks to being able to take 5,000 spectra at one time, covering this very wide swath of sky. And so what you see here is that these little blue outlines within the yellow circle are all 5,000 of the positioner patrol radii. And so every time DESI points the telescope at some field, we jiggle all those positioners around so that they find the right galaxy to look at, and then you take your spectra. So here's, from a little bit more of a hardware perspective, what this actually looks like. So this is what we call a petal. So DESI's focal plane consists of 10 of these petals that form into a circle like you saw before. And each of these petals holds 500 of these fiber positioning robots that target the galaxies and the stars that we want to get spectra of. And so this is showing a petal that's been partially filled with the positioners. And so I'll show a video of what this actually looks like when they move around. So hopefully this is playing, but these positioners have little caps on the ends of them, so we would take those caps off before we would do the actual astronomy with them. But you can picture if you have now 10 of these petals joined together into a big circle, every single hole in these petals is filled with one of these 5,000 robots that can jiggle around a little bit to target the right stars and galaxies. And to give you a sense of size, the diameter of the focal plane is about 1 meter across. So one of these petals is kind of half a meter in size. And if you think about all of this, one amazing thing that's always scared me a little bit about DESI is that in the DESI focal plane alone, there's about 600,000 moving parts. And so that's quite an ambitious technological feat, because you may see in the press or the media, a lot of, for example, NASA missions will always brag about how they're such safe and risk-averse experiments because they have no moving parts. And DESI is the exact opposite of that, where we have 500,000 moving parts crammed into a tiny space, and we have to make them all work together with each other. Let me try to advance the slide. Okay, so again, this is really a big technological milestone for 3-dimensional mapping of the sky with spectroscopy, because Sloan had this very arduous process where they would have to drill holes in these metal plates and then by hand plug all of their fibers into those plates. And this was really a limiting factor for what could be done. But now that we have these robots that can reposition themselves so quickly, you don't need to drill a plate, you don't need to manually do anything. It's just all software that controls these robots. So that's a huge breakthrough. Okay, so I wanted to mention, I've said now that DESI is looking at specific galaxies. It's not just looking at random points on the sky. So there's been a huge amount of work in what we call our DESI pre-imaging campaign. So we need deep and wide sky maps that can even allow us in 2 dimensions to select our targets that DESI will look at. And so this is something that I've worked on for over 5 years now. So it's something I like to highlight because it sometimes gets overlooked. But DESI's pre-imaging sky maps for target selection are actually state-of-the-art, and they're deeper and wider than anything before, deeper than, for example, Sloan's imaging, deeper than Pan-STARRS. So it's really a huge accomplishment unto itself, just the pre-imaging that we've done. So right, DESI is a targeted survey. You need to have in advance a list of galaxies that you tell the robots to go to. DESI pre-selection of its targets is based on two-dimensional sky maps from 4 telescopes. So actually we're using, again, the same Mayall 4-meter telescope at Kitt Peak that DESI is now installed in. So before we dismantled everything and rebuilt it with DESI, we had an imager on there that would just take nice pictures of the sky for us. There's this WISE satellite from NASA. That's actually one of my focuses within the DESI collaboration, is taking the full sky infrared data that WISE gives us at, say, 3 to 5 microns, and using that in DESI's selection of its galaxy targets. The Mayall telescope has a southern twin 4-meter telescope called the Blanco 4-meter in Chile at Cerro Tololo Inter-American Observatory, which I visited several times to go observing there for our DESI surveys. So we also use that for the more southern parts of our surveys. And then there's also the Bach telescope at Kitt Peak, which is right next to the Mayall telescope in Arizona. So if you actually add everything up, just the DESI pre-imaging surveys required performing something like 1,000 nights of observing combined at these 3 ground-based observatories. So this was quite a monumental effort unto itself, even just to get to the stage of having the targets for DESI to look at. With DESI pre-imaging, we've cataloged more than 1.5 billion sources, making it one of the largest ever astronomical catalogs to be made. So now the trick is that DESI must choose the best 35 million sources among those 1.5 billion to get spectra of. And I did want to highlight before I leave, I personally observed for something like 40 of these nights during the DESI imaging surveys. I had a combination of the Mayall telescope in Arizona and the Blanco in Chile. And this is a picture I took of myself. There's this mirror as you're going up the hill, walking there from the dorms to the telescope. I don't know if you can see my mouse, but anyway, this is me here in the reflection. This is a Blanco 4-meter telescope up in the corner. Then you can see this very nice scenery here of the mountains, and it looks like it could be a pretty good night. There's not too many clouds overhead. I would also just note that this is at like 7,000 feet elevation. This is quite a steep hill to walk up, so you really feel it when you're walking up from the dorms to the telescope there. It's much more tiring than you might expect it to be to walk up a hill if you were just at sea level, for example. But this is a very nice site to go to, although it takes a lot of travel to get there. So it's like 3 plane flights and then a pretty long ride, which has a lot of the late portion of it on steep gravel roads to get up to this observatory. Kitt Peak is kind of the opposite of that, actually, where it's about an hour's drive outside of Tucson, which is a pretty substantial city, and the roads are all very nicely paved up to there. So in terms of tourism or potentially visiting, I would recommend Kitt Peak over CTIO just as a matter of convenience. So just to show a little bit of what we get out of this imaging surveys and what eventually will then become the sky footprint that we look at with DESI itself. This is an image showing the entire sky in celestial RA-det coordinates. And the areas that are colored in, say, blue and yellow and red are those that we have this imaging data for to select our targets. It covers about 20,000 square degrees now. But some of that data we have from archival sources. It's actually too far south for us to look at because Kitt Peak is at +32 latitude. So anything below declination of -30 is too far south for DESI to look at, but everything above we can look at. Don't worry too much about the acronyms, but essentially DESI will look at everything that's visible above dec -30 and that avoids the galactic plane. So within about 20 degrees of the galactic plane of the Milky Way. We just cut that out because there's so many stars contaminating our selection of the distant galaxies that we really most want to look at. So right, DESI will look at something like 14,000 square degrees in total over 5 years. I just wanted to mention what exactly are the types of celestial objects that we're looking at with DESI. So there's what we call luminous red galaxies, which are old red elliptical galaxies, and there's about 4 million of those in total. There are quasars, which hopefully you've heard about in some of your prior talks given at this society, but they're galaxies with luminous, actively accreting central black holes. DESI will look at about 2 million of those, and those are extremely useful because the central black hole makes for such a bright emission that you can see those very, very far out across the universe. So they're very powerful for going to high redshifts and to mapping a large volume of the universe that's very distant from us. The sort of core part of DESI's galaxy survey is what we call emission line galaxies. So these are actively star-forming galaxies. They're largely at redshift above 1, which is unexplored territory for dark energy. Prior surveys that have been precursors for DESI have been limited to lower redshifts, so objects that are more nearby to us. And to do this, you have to go very faint. So just to give you a sense of the magnitudes here, DESI's emission line galaxies will go down to G magnitude of about 23.6. And so typically people quote for what's a visible eye star, something like 6.5 magnitude is the limit there. So if you think about it, we're going down like 7 million times fainter than that. We're very, very faint objects. It's amazing that we can get spectra of them. And it's because most of their flux is coming out not in the broad continuum, but it's concentrated in a couple of emission lines, which gives us a hope of detecting their redshift in the spectra. So when we get spectra of these, you see basically nothing except you hope for a couple of faint emission lines at the right place. So it's a very tricky business to try to observe such faint objects that are so far away from us. And then there's this bright galaxy sample that we'll do, which is about 10 million relatively nearby galaxies. Basically, the idea here is that DESI is on the telescope all the time. You can't do anything else with the telescope. So you might as well look at something while the sky is relatively bright, for example, twilight or when the moon is out. So you might as well look at these brighter galaxies that are easier to observe. Just to put a picture to these words of the different types of things that DESI will look at on the sky, they actually look kind of like what you might expect. So let me see if I can point to a few examples here, but if you can see my mouse in the center, there's this red circle labeled LRG, and indeed it kind of looks like a reddish galaxy that has some fuzzy extendedness to it relative to a point-like star. So it's kind of like what you would imagine. Same with the BGS, that stands for Bright Galaxy Survey. And indeed, if you look at the objects labeled BGS here, circled in yellow, those are big, bright galaxies that we can do relatively easily when the sky is brighter or conditions are worse. Then you see, if you can see these white circles labeled with ELG, the emission there is almost imperceptible. You'd have to zoom in to even convince yourself there's something real there. But these are very, very subtle in the imaging that we have. And that's actually because they're kind of harder to detect in the imaging than they are in the spectroscopy. Again, because most of the emission is in these few localized lines at certain wavelengths. And here we have broad filters that we're looking in. So if you want to explore more of this, I highly recommend this tool that was built by my DESI colleague named Dustin Lang. The URL is listed there. It's a really great interactive sky map that lets you zoom in, zoom out, overlay all kinds of useful data sets. You can overlay these targets just like I've shown here in the screenshot. You can overlay other fun catalogs like Gaia you may have heard of. It's a very, very powerful tool that I use basically for all of my research constantly, regardless of whether it's DESI research. So I suspect that for folks like you who are doing your own observations and who are knowledgeable about astronomy, this could be a really fun and useful tool to play around with in relation to just learning more about different aspects of astronomy or in combination with the observations that you do yourself. So some basic numbers about the survey. So DESI takes relatively long spectroscopic exposures, 15 to 20 minutes typically. The field of view, as I mentioned, is huge, 7.5 square degrees. So if you cost that out in terms of we want to cover 14,000 square degrees total with 5 passes, so you'll sort of visit every place on the sky 5 times. That turns out to be about 10,000 pointings, which at 15 to 20 minutes each gives you the 5 years that we need to actually complete our mission. One other thing to note is that DESI observing will be highly automated. So we have a real-time exposure time calculator. So in real time, it measures the image quality, the sky background brightness, and so forth in order to adjust the exposure times on the fly. So we don't just go there and say, okay, 15 minutes. We try to be very smart about how we utilize every last bit of our time. And there's a next field selector piece of software that will automatically make the decision about what sequence of sky locations we visit based on various parameters, like what has been mapped before, for example, in the previous year, now that we're in the second year or something like that. So that was the last of what I wanted to say about the survey. And I wanted to just end with a few slides about the DESI installation and commissioning. I wasn't really involved with the installation, but I was involved with the commissioning of the hardware. So sort of testing it out to see how it works and make sure it actually works on the sky. And I just wanted to mention this because it was really a monumental effort unto itself to basically take apart the entire Mayall 4-meter telescope, which had been intact since the early 70s when it was built. So, you know, like 45 plus years ago now, and then reinstall totally new hardware for the specific purpose of DESI. And so what you see on the left here is the fact that we actually removed the entire telescope top ring and corrector assembly that used to be on there and replaced it with a completely new one for DESI. So this is showing on the left a giant crane that we brought in that came in through the dome slit on the top, picked up this top end, which weighs of order 10 tons, and brought it out of the telescope entirely and down to the ground. And so just to give you a sense here, the Mayall telescope building is about 180 feet tall. So it's really a huge structure. It's quite amazing to see this take place. This happened a couple of years ago. I forget the exact dates. And just to give you a sense of scale, since you can't really tell from the picture on the left, but the picture on the right shows the new top ring that was lifted up and put on the telescope floor near, you know, the mirror and everything else. You can see on the right just how huge that is relative to the people standing there, for example. Just to give you a sense of scale. I mean, this is really, really massive equipment that we have going on here. Right, so as I said, we took out the old corrector entirely and put in a new one. And you can see, for a sense of scale on the left, that's the corrector being lifted up off the ground with a crane. And you can see people standing in the background. So this corrector is, you know, bigger than a large person. Quite huge. And inside of it, there's a series of 6 large lenses on the order of 1 meter in diameter each. And so just from a sort of optical sciences perspective, this is kind of a remarkable feat to get these, you know, millions of dollars worth of lenses polished all correctly in order to deliver good image quality over a field of view that has a diameter of 3 degrees, which is very, very large. So I don't know exactly what lenses are being shown here, but this is some subset of them. You can see that the clean room employees who are partaking in some combination of the polishing and or testing are shown as seen through that combination of lenses. Just showing a little bit more about what the hardware all looks like when we've put it now in the Mayall telescope building. So on the left is what we call the spectrograph shack. It's not really a clean room, but it's like a semi-clean room. So it's this special environmentally controlled room where we try to keep the temperature constant. And there are these big racks of all the spectrographs. So in order to get 5,000 spectra at once, DESI needs to have 10 identical copies of the same spectrograph. And that's what you're seeing here. Each one of these 10 can take the spectra of 500 objects at once. So as you might guess, the petals that I showed before, each petal is connected via fiber optic cables to its corresponding spectrograph, where the petals are at the prime focus of the telescope, and the spectrographs are in this special spectrograph shack that's like 40 meters away. Just to give you a sense of size, the sort of metal silver bar that you see in the center of this rack of spectrographs is kind of at like waist height for a person. So this is a lot of equipment going on here in order to get all these spectra at once. And then on the right, you see what I've always found to be a very cool picture, but this is the actual installed full focal plane DESI at the Mayall telescope. And what you're seeing is the 5,000 positioner tips inside of the very dark corrector barrel. And so that's really cool to see. It would be even cooler to have a video of them moving around in here, but I don't know if we have such a thing. So, right, we have all this new hardware, but we have to test it out to make sure that it works, for example, that it'll meet all of our requirements in order to deliver our cosmology and fundamental physics science that we've promised to do with DESI. And so this was the first night of what we call the DESI commissioning camera. This is the control room. DESI built this big brand new control room in the Mayall building because we knew that DESI is such a complex instrument. We would have to have lots of experts on hand at once, filling the room in order to get it all up and running. And so the first flight with the DESI corrector with the commissioning cameras, where we had mounted commercial grade cameras, instead of having all of these fiber robots, we just put simple cameras behind the corrector to see what the image quality looked like. This was April 1st of 2019. And a fair amount of luck was involved in this, but on the first night, we happened to have really, really good astronomical seeing, really low turbulence in the atmosphere, and we got 0.7 arcsecond image quality right off the bat on the first night. And so you can see I indicated with a red arrow, I'm standing in the back of the room there during this first light DESI milestone with the corrector. And a bunch of these people here are the key people who do things like the instrument control software that makes all these different pieces talk to. Here's first light with the DESI commissioning camera. So while I was in the back of the room there on that first night at the telescope, I was post-processing the images to try to make pretty pictures. And one of the first things we looked at was M51, the Whirlpool galaxy. And this is the post-process image that I made that ended up being used in a lot of our press releases for DESI about the fact that the corrector really was delivering its promised excellent image quality. So people were really excited that we were able to get such an amazing looking image on the first night. So of course, DESI isn't just about taking images, it's really about getting the spectra of these galaxies. And so there was a down period between spring and fall of 2019 where some more hardware updates were made on the installation side. But then in October, the commissioning team came back to do first light with the actual spectra. And so here on the left is our afternoon planning meeting where all the experts are sort of trying to figure out how it is that we're going to go about meeting our goals for the night. And then a few hours later, there's a picture of raising glasses that I think probably just have water in them. I don't think we're allowed to have alcohol at the telescope. But we did on the first night get our first spectra. In the very beginning, we actually weren't moving the fiber robots. We were just letting them sit where they were and moving the telescope around. So our first spectra were a lot of pictures of the blank sky, basically. But a few of them did happen to have stars just because we have so many chances to hit a star in our field of view. So the spectroscopic first light was 2019, October 22. So close to a year ago now. And through DESI commissioning, we now already have hundreds of thousands of spectra of stars and galaxies. And so this is one example. I don't really know how much I'm allowed to share since it hasn't been formally published yet, the spectroscopic data at least. But this is an example of what one of our luminous red galaxies looks like. This is a kind of an unusually distant one at redshift of 1.29, taken during DESI commissioning. And you can see that the red is the data and the black is the model. And so we're getting tons and tons of signal to noise here that will enable us to measure a redshift nicely for it. Right, and so DESI's primary mission is to get these 35 million redshifts to do its cosmology, but the spectra have a huge wealth of bonus information for other types of astronomy that I'm particularly looking forward to. My own science interests are not in cosmology, actually. I'm much more interested in like Milky Way stars and brown dwarfs and stuff like that. So I'm very excited about having this huge data set with 35 million objects and sort of looking around to see what the unusual or unique ones are in there, separate from the cosmology. And of course, examples that you can do with, say, stars are spectral types and chemical compositions. That's beyond just redshifts. So to conclude my presentation, DESI is the result of combined participation from a lot of member scientists in many countries. It's something like 700 scientists total, although any one specific thing like the hardware or commissioning will have a much smaller core team of people working on it. I would also note that about 10% of these scientists are part of the DESI UK consortium. So the UK is a major partner in DESI, and I was able to find online the list of these institutions that are part of this. It's Durham, Portsmouth, UCL, Edinburgh, St. Andrews, Cambridge, and Warwick. So I would strongly recommend that your society in the coming year or two would reach out to some of these UK scientists, particularly the ones who might be able to provide more of the insight about the theoretical aspects of the cosmology and how that's really done, because that's not what I personally work on. And it would be great if you would have, consider having someone like that from the UK consortium of DESI discuss some of the early initial science and cosmology results a year or two now. So I'll leave it at that, and we can have questions or whatever else is on the agenda for the meeting.
Right, thank you, Aaron. That was absolutely fascinating, and it's nice to see or hear a presentation which takes you from the inception of a project and through its commissioning, and then right to the point where you're going to start producing some results. Could I ask you to stop sharing your screen?
Yep, sure thing.
And then we can go back to gallery mode. And what we'll do now is we'll take questions. Whilst people are framing their questions, I've just got a quick question. How much data does DESI produce in a night?
Yeah, that's a really good question. It's actually not that much of data in terms of raw volume. It's like in terms of total raw data, it's maybe like a few terabytes per year, which is quite a lot less than imaging surveys. Like with the Dark Energy camera, you could easily produce way more than that, and that's simply because DESI takes such long exposures. It's taking 20-minute exposures, whereas with some of these gigapixel imagers we have nowadays, like Rubin LSST or DCAM, you can get billions of pixels in 15 seconds or a minute. And so that's really the difference. But I would say that DESI is still a very data-intensive project, just because it's a very large and complex and rich data set of these 35 million spectra. So even though the sheer data volume isn't a lot, data analysis is really a core theme for us.
Yeah. And on a typical night, how many people would be actually manning the observatory?
Yeah, that's another really good question that we've been forced to reconsider now that we've had this pandemic situation that's forced us to shut down. For commissioning, as I said, we built this new control room because we knew lots of experts, like 6+ at a time, would be in there at once. The original plan was that in normal operations, once everything has been tested out, you would have 3 collaboration scientist observers every night, plus the telescope operator, who's an employee of the observatory who is responsible for the safety of the telescope. So that'll be 4 people. But now that we've had this pandemic and there's travel restrictions, we're trying to move as much as possible to remote observing. And I'm sure this is a theme that's common to basically all observatories nowadays. So we'll see how it goes, but there still are going to be at least 2 people in the building at all times when we're observing at night. And we have 2 control rooms, so we can have each person in a separate part.
Okay, thank you for that. Okay, ladies and gentlemen, over to you. As usual, if you can electronically flag a hands up, or if you want to risk trying to attract my attention by waving at me, please do so. So has anybody got any questions for Aaron? So Gary, can you unmute yourself, please, Gary?
Yeah, I think I'm on. I'm off mute.
Okay, can we have your question, please?
Well, a couple of questions, really. Can you just explain a bit more how the fiber robots work? Because we saw them rotating, but can they also move radially? And a second question would be, is out of the 5,000 robots, how many are actually on target every imaging sequence? Is it all 5,000, or is it just a percentage?
Yeah, so the robots can move in 2 axes, as you basically correctly guessed. They call it sort of theta phi type motion. So you can move around, as you said, what I showed is kind of going around circularly, but you can also move radially around. One interesting nuance of this is that actually the patrol regions of the fibers overlap one another. So you have to be extremely careful not to slam the robots into one another as they're moving around. And that's something we're still working on very actively. The second part is that, yes, in every exposure, we have a specific place for every fiber to go, but some fraction of them, like a few hundred per exposure out of the 5,000, are dedicated to going to blank sky locations so that we can calibrate the sky emission and subtract that off from what we see from the galaxies and the stars. So it's, you know, every robot is going somewhere specific, but some of them are going to blank sky.
Thank you.
Okay, thank you, Gary. Has anybody else got a question? Trevor Worrell, can you unmute yourself, please?
Hiya. Just about the robots again, how do you ensure like they're actually pointing exactly where you want them to? Is there any feedback to say, you know, they're actually on that area of the galaxy or the sky that you want?
Yeah, really great question. That's one of the very hardest challenges that we have for DESI. I'm getting some sort of feedback right now. I'm not sure.
It's okay, I've dealt with that.
Okay. But one of the things, you know, commissioning was 4 months for DESI, and that was basically the thing we spent almost all our time on, is that it's really, really hard to convince yourself that you know where these fibers are going. One mechanism that we have to deal with that is that the fibers can actually be back illuminated. So coming from the area of the spectrographs, you can send light through the fibers, and it goes down from prime focus back towards the primary mirror. And we actually have what we call a fiber view camera that's at the cast focus. So, you know, kind of behind the primary mirror, and it looks up towards the focal plane. And so it can look and see the spots of light that show exactly where these robots are. And that's really important to us, because if something goes wrong in the software, we need a way to find where these robots actually are. And that's really the only way we can do it, is by back illuminating them and then looking at them through the special fiber view camera system that we have. Okay,
Trevor, you've got a follow-up question.
Yeah, just one final one. I hate to mention it, but Starlink. I just dread the impact on professional research, never mind amateur astronomy. And you just don't know what to believe. What's your thoughts on the Starlink project and the effect that potentially it could have on projects such as this?
Yeah, you're absolutely right that it's a big concern for all ground-based wide area survey type of projects like DESI. The other ones that come to mind, of course, are Rubin, LSST, which is going to be impacted by these. I think our preliminary calculations is that, of course, for DESI, it would be better not to have any Starlink bright satellites coming out, but it's not all that devastating in terms of it's just not super common for one of those to cross over one of our fibers while we're integrating. One issue, though, is, you know, we do want to know about when that happens, because if a bright satellite contaminates our faint galaxy spectrum, that's something we want to know about for our data analysis. And so we actually have a very fancy high-grade commercial camera that's mounted on the top ring of the Mayall telescope. We call it the pointing camera, and that has a 3-degree field of view that can, in real time, watch the entire DESI field of view with images that, you know, they're low resolution, so they have like 8 arcsecond pixels or something. But one thing that I personally have been working on is using this pointing camera, this commercial camera that's mounted on the top ring, in order to find satellite streaks and use them to know when they've contaminated our spectroscopic data.
Okay. One more question from me then, please, Aaron. And that's, after the 5 years of the survey, what will happen with all the equipment?
Yeah, that's definitely something we've been thinking a lot about already, even though it is about 5 years into the future. My personal take on this is that, you know, it took a 1.5 years of disassembling and reassembling this entire telescope to get DESI put on to the telescope. So we really don't want to, in my opinion, go back and install something totally different and totally new unless there's some immensely powerful rationale for doing that. So I think that we do want to find sort of a new scientific mission for this same DESI hardware at the Mayall telescope moving forward into the future. And there are a lot of different ideas about that because DESI is a very multi-purpose type of instrument. You could use it, for example, to look at hundreds of millions of stars instead of these 30 million galaxies. So personally, I'd be very interested to see if we could get an extended mission for DESI that would have a mission more focused on scientifically looking at stars in the Milky Way. So I think that would be really great. And so it's really a matter of finding the right partner institutions to come in and make it happen. I suspect we will, but I'm still not sure what the exact science case will be.
Okay, Peter Lloyd, can you unmute yourself, please?
Thank you, Paul. Thank you, Aaron, for a fascinating talk. You say you take 5,000 spectra every 20 minutes. That to me is 15,000 spectra an hour for maybe 8-hour nights. That's roughly 120,000 spectra a night. How on earth do you look at such a huge number of spectra?
Yeah, that's a big challenge we've had, is trying to put in place the sort of data analysis and data visualization tools to be able to even understand this data set that's so complex coming off the telescope. And so we have a very powerful supercomputer in Berkeley, California called NERSC that's provided by the Department of Energy of the United States, which is the prime funder of DESI to begin with. And so we have an automated data transfer system that takes the data right off the telescope, transfers it to NERSC within a matter of minutes, the supercomputer center, and automatically processes it very quickly. So the idea is that you have your fully processed data, including redshifts, by the time you wake up for breakfast the next morning. And then we also have a real-time spectroscopic reduction module that we call Night Watch that runs at the mountain as the data come out. And so that creates a sort of visualization data panel that can be watched by the DESI observers in real time to sort of keep an eye on whether anything's going wrong. But it is a big challenge when you have such a complex instrument to try to notice when something is going wrong as quickly as possible, because sometimes it can be not obvious.
But presumably, even after they've been through this supercomputer, there's still quite a lot of things that a human has to look at.
Yeah, I think one goal, is of course to try to automate as much as possible, but there are some bottlenecks that will require visual inspection. So for example, one of our target classes is these very distant quasars, and there is a part of the DESI procedure where we're supposed to have a rapid turnaround of people visually inspecting every single one so that we know whether the faint object we targeted is really a quasar and whether it's worth going back to look at it with more telescope time. And so that you're right that this visual inspection is something that's in our procedures, and it's something we worry about as far as being able to keep up with the sheer data volume. But there will be a lot of spectra that no one ever looks at. That's because we're mainly interested in extracting just the redshift, which you can largely do with software. But I do think this opens up a lot of possibilities for sort of like citizen science or crowdsourcing when the data goes public, to just have a lot of interested people looking at the data, and you may find really big discoveries that have been missed because we just couldn't keep up with looking at all of it.
That was what I was wondering about. Thank you.
Okay, ladies and gents, I'm going to do one more pass, try and spot anybody else who... Oh, Gary Goldthorpe's got another question for you, Aaron. So unmute yourself, Gary.
Yeah, I'm unmuted. Just slightly follow up from Paul's question about what you're going to do in 5 years. Would there be any benefit in actually moving the camera to Chile and actually doing the rest of the Southern Hemisphere?
Yeah, great idea. And you may not be surprised to find out that there's been a lot of discussion about that among the scientists here in Arizona and here in Chile.
Because obviously it's had a big camera on in the past, and it's the same design and as the Mayall telescope. So
yeah, people are very interested in that. The biggest concern is just the sheer amount of time and effort it would take having basically both telescopes down in order to take this instrumentation off of one telescope and then move it to the other. So it's a question of whether there's enough rationale to justify losing all that scientific observation time with the uninstallation and moving and shipping and reinstallation.
Okay, Gary. Okay. and Tony Morris. Can you unmute yourself, Tony?
Unmuted, Paul.
Thank you. Can we have your question?
Hi, Aaron. When you were showing the histogram of the distribution of the distances between the galactic centers, you're actually mapping in 3 dimensions with your imaging, but your histogram is basically showing a 2-dimensional view. So how do you correlate the 3-dimension to the 2-dimension just for display purposes?
Yeah, so there's a version of that histogram that you can make just from a 2-dimensional map. But of course, the power of DESI is that we have an actual 3-dimensional map now. And so we can do those types of density analyses in truly 3 dimensions. And so, yes, that sort of cartoon collapsed it into 1 dimension for the sake of visualization. But there's a lot of work on the sort of cosmology theory side from many people in the DESI collaboration. Not me, that's not really my thing, but certainly a lot of the UK consortium specializes in this. But you have this rich 3-dimensional information, and you want to extract as much data and as much value as you can as possible. So indeed, you really want to make the most of the 3-dimensional nature of the data set beyond just a simple 1D histogram. And so there's a lot of work, computationally and mathematically going on to figure out how do you optimally do that.
Okay, right, thank you.
Okay, Tony. And ladies and gents, as I was saying, I'm going to make one more pass just to see if anybody wants to ask an additional question. And, oh, go on then, Gary. This has got to be the last one, though. Go on, Gary. Gary, were you waving?
Yes, I was waving. Yeah, I'm just coming off mute. You said you got obviously 5,000 fibers, but you'd only got 10 spectrographs. So how does each spectrograph looking at 500 fibers then?
Yeah, that's correct. So each spectrograph has 3 CCDs, one for each of 3 different wavelength bands. And so you have one petal in the focal plane mapping its 500 fibers that run down towards one of the 10 spectrographs, which then collects 500 of these spectra at a time. And the way it works in practice is that each spectrograph has 3 detectors, and on each detector, you have a situation where sort of the row direction is wavelength and the column direction indexes which fiber in the focal plane is being looked at. And so you get these 2-dimensional images that you can extract simultaneously 500 spectra from at once.
Okay, Gary.
Thank you.
Thank you. Ladies and gentlemen, I think we've worked Aaron really hard this evening. Thank you very much, Aaron. And in our usual Mexper and Swinton Astronomical Society manner, can we give Aaron a big thank you?